of K simplices. So a K simplices is given by K plus 1 vertices. So for example, so one zero simplices is just a vertices. One simplices is a line. A two simplices is a triangle. A three simplices is a tetrahedrons, and then you can go all the way up. And then a simplicial complex is just like you combine this object. Then we call it a simplicial complex. And then in this talk, I would like to emphasize that you could define a directed version of this simplicial complex. And we can define the directions by like assigning. So this is, if it's a positive direction, it's plus. If it's a negative direction, we include a minus here. And this is quite crucial. Consider oriented simplicial complex is quite is a key in our result, because by doing that we introduce a minus sign, so that it introduces this decoherence and then cancel out many of the terms, and that's why we put in a way that intuitive way to understand why, even though a high dimensional homologies contains so many edges and faces, but still we could have efficient quantum algorithms because they cancel out through this positive and negative orientation. And then we can define that's called the chain group. The chain group is just like spanned by your simplices. And remember that this simplices was indexed by the vertices. Okay? And then once you have a chain group, then you can define this called boundary operators that you take from the K chain group to K minus 1 chain group by this. So this is just to erase the case point and introduce a phase if it's 1. So this is how you did it using example. So if you look at this 3 simplices, then you just follow this calculation, then you will have a minus sign here. So, okay, so this is the so-called the boundary operators. And then we can define the key object. So this is called the homology group. It is defined as like the kernels of your case boundary operators. So this is ZK is called the cycle group. This is just terminology. You don't need to worry too much about that, but at least you know this boundary operator is a linear operator. So you can define its kernel as well as its image, right? So this BK is the image of K plus 1 boundary operators. And then from this, you can define the homologies. And the reason that we care about this homology is that these homologies, the rank of homology would give us the Betti numbers, okay? And if you think deeper about the definition of homology, so this actually characterizes the case dimensional holes in your space. Okay. So now you could, from here, I think the important things to remember is that the case Betti numbers, to find the case Betti number is equivalent to find the rank of your homologies, right? Okay. And then another related object is in this domain is called the Laplacian. The Laplacian is defined again by the boundary operator. So that's why I'm saying that boundary operator is very important here. And by the whole series these boundary operators also, like the kernel of boundary operators is isomorphic to the homology, the case homologies. Okay, so once I introduce those terminologies, then we can go over some of the known results. So actually, the first one is very famous. So this is by Seth Lowy and his collaborators, Paro Zanadis from USC. So they have this science paper in 2016. This is the first efficient quantum algorithms in TDA, topological data analysis. And you can see that this N is the number of vertices. So you can see that if they use that to estimate it normalized Betti number, and so ignore this term. So this would be canceled out. So it's polynomial algorithms in terms of number of vertices. And then there are a few follow-up results, right? So it improves slightly about this dependency on N. And the recent one is by Gideon, Mario Berta, and a Caltech student. They, instead of improving time complexity, they improve the space complexity, meaning that number of qubits that you need to use in your quantum algorithms. But I would like to highlight that those constructions is actually quite non-trivial in a sense. So the way they construct this boundary operator needs to go through multiple steps. For example, you have to, because this boundary operator is not Hermitian, so they have to do like Hermitian embedding and then use Hamiltonian simulation technique to create this kind of operators in the quantum domain. So in my opinion, even though this algorithm they work, that is not as direct as our result, because we use quantum work, and you can see that if you use quantum work, it becomes very natural in a sense. Okay, so this is our main result. So the main result is that we could construct a quantum work unitary so that we can use it to implement this projector to the case homology group, and then you can count the number of count the Betti numbers. Okay, and then of course we could show that the previous one says that if this exists, we can efficiently implement the projectors. And then our next result is saying that indeed we can construct this quantum work unitary very efficiently for the clique complex. And clique complex, it's actually already quite large in the Simplicial complex. Okay, so I have another 10 minutes, so let me quickly go over the proof steps. So basically, the proof steps is not difficult. So given simplicis, we can construct. We could already, from that structure, we can construct a random walk on it, right? And so we can construct a transition matrix on this simplicis. And then the next step is just directly quantize those transition matrix, right? And then once you quantize it, I think this is a key step, is that we can, using our quantum work unitary to construct this Laplacian. And again, it's not too difficult if you if you know the relationship between this Laplacian and the change